Hello, friend. Welcome to Science for Sleep. Tonight, we begin with something so familiar that it is easy to stop noticing it. The ground beneath your feet, the floor beneath your bed, the road outside, the dark fields, the sidewalks, the stone, the packed soil, the quiet weight of the world holding still beneath every ordinary day. Most of the time, Earth feels finished from where we live on it. It feels settled, flat enough in the places we build, solid enough to trust without thinking. You place your weight on it, and it answers by staying there. You do not usually need to wonder what lies far below a driveway, a backyard, a sleeping town, or the slow black water beyond a shoreline. The surface gives the impression that the planet is simple at the top, and perhaps simple all the way through. But Earth is not simple all the way through. Beneath the thin outer layer where all known life lives, the planet continues downward into heat, pressure, slow-moving rock, liquid metal, and a hidden center compressed by enormous force. The crust we stand on is only a small outer part of the whole Earth, more like a thin shell than a deep solid block. And far below that shell, in darkness no human eye will ever directly see, a great layer of liquid metal moves around the deeper center of the planet. That hidden motion matters more than it may first seem. The movement of liquid iron in Earth's outer core helps generate the planet's magnetic field, and that field extends far out into space around us. Many people think of protection as something that comes from above, from clouds, from the sky, from the atmosphere, from distance. But part of Earth's protection begins below. Deep below. The planet under your feet helps create an invisible magnetic shield around the world, one that shapes how Earth meets the charged particles streaming outward from the sun. So even now, in a quiet room, or under a blanket, or resting while the day softens at the edges, you are lying on the outer skin of a planet whose unseen interior still affects the world above it. That is one of the gentlest strange facts about Earth. Some of the conditions that help make life possible are connected not only to the air around us or the light above us, but to processes unfolding thousands of kilometers below the surface, in places no person has ever visited. And yet the surface remains calm. A sidewalk does not tremble with that knowledge. A field at night does not look like the roof of a layered world. A sleeping city gives no sign that, far below its streets and pipes and foundations, the planet keeps descending into regions of greater heat and weight. The deeper Earth does not announce itself very often. It simply continues, quietly, constantly, beyond the reach of ordinary experience. If you enjoy these quiet journeys, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find their way to this calm corner of the world, one sleepy traveler at a time. There is something comforting in that scale, not because it makes us large, but because it reminds us that the world is deeper than the part we usually have to carry in our thoughts. Beneath the errands, the messages, the lights, the weather, the clocks, and the small pressures of a human day, there is a much older structure holding everything up. A layered planet, a slow planet, a planet with an interior that formed long before roads and roofs and names, and that still moves in ways too gradual for the body to feel directly. Children have joked for generations that if you dig down far enough, you might come out on the other side of Earth. It is the kind of idea that stays in the imagination because it takes something hidden and makes it simple. Just keep going down. Just keep digging. But the real truth is quieter and more surprising than the joke. Humans have imagined tunneling deep into Earth for a very long time. Yet even our deepest attempts have only scratched a tiny fraction of the outer shell. The world below us is far deeper than our instincts suggest. And that makes the question even more beautiful. If we have gone down so little, then what exactly lies below us in all that unseen depth? How far have we truly reached? And what stops us from going farther? For now, it is enough just to rest with the feeling of it. The gentle fact that beneath every step, every house, every road, every sleeping coastline, Earth continues downward into hidden layers we rarely picture, but always live above. For a long time, people have joked that if you dig straight down through the Earth, you might eventually come out on the other side. In the United States, that old joke often ended with China, not because it was meant as geography, but because it gave the idea a distant and almost storybook destination. It turned the hidden world below our feet into something playful and imaginable. A child could understand it immediately. Just keep digging, keep going. Somewhere beneath the grass, beneath the stones, beneath the roads and tree roots and buried pipes, the planet would open into a long path through itself. But what makes the joke last is that it brushes against a real human curiosity. People do want to know what lies below, not just a few feet down, where soil turns cooler and denser, but far below that, below bedrock, below the places minds can reach, below the level where groundwater rests in cracks and pores, below everything that feels connected to ordinary land. There is something deeply natural about wanting to know how far Earth goes, and whether the ground beneath us is only a thin layer over something larger, stranger, and more difficult to imagine. In truth, humans have dug downward far more seriously than the joke suggests. We have mined deep into mountains. We have drilled through rock in search of oil, gas, heat, metals, and scientific knowledge. Engineers have sent drill bits into the crust under deserts, plains, and ocean floors. At the surface, these efforts can look impressive, industrial, even heroic. Towers rise, pipes descend, machines grind. Rock comes back upward in cylinders and fragments, carrying news from below. And yet, compared to the full depth of the planet, even our deepest drilling barely counts as a beginning. The deepest human-made hole ever drilled was the Kola super deep borehole in northwestern Russia. It reached a depth of a little over 12 kilometers. 12 kilometers sounds immense on a human scale, and it is. It is far deeper than any building is tall, far deeper than any ordinary cave, deeper than almost any place a person would ever imagine traveling beneath the surface. But Earth itself extends down for thousands of kilometers. The distance from the surface to the center of the planet is more than 6,000 kilometers. So even our deepest borehole only entered a tiny fraction of Earth's full depth. That contrast is one of the most humbling facts in geology. We live on a planet that feels huge from side to side. Oceans spread wide. Continents take days to cross. Mountains rise beyond clouds. But in the downward direction, Earth becomes even more astonishing, because the part we can directly reach is so shallow compared to the whole. Human beings have explored more of the moon visually than of the deep Earth physically. We have seen farther into space than we have traveled down into our own planet. Why have we stopped so early? The answer is not lack of curiosity. It is that Earth resists us more with every kilometer. As drilling goes deeper, temperature rises. Rock at depth does not stay cool and cooperative. It grows hotter, and that heat begins to affect the machinery itself. Metal expands, tools wear down faster, equipment becomes harder to manage. The rock can behave in ways that surprise engineers, becoming weaker, more fractured, or more plastic than expected. In some places, pressure and heat together turn the drilling process into a battle not just against depth, but against the changing nature of the Earth itself. Even the borehole walls can become difficult to keep stable. This is part of what makes deep drilling so fascinating. It is not just a matter of making a longer drill. It is not like extending a straw deeper into a drink. The Earth changes as you descend, and those changes begin long before anything dramatic or mythical appears. There is no sudden cavern of fire waiting just below. No giant hollow chamber, no hidden doorway into the center. Instead, there is a gradual rise in heat, pressure, and difficulty, until the conditions themselves become the barrier. And that barrier arrives very early relative to the full planet. Even if humans built better drills, better cooling systems, better materials, and more powerful rigs, reaching the core would still be unimaginably difficult with present technology. The crust alone is far thicker than most people picture, and beneath it lies the mantle, which is not empty space, but an enormous region of hot rock under great pressure. To drill all the way through Earth's crust and mantle and then into the core would not simply be hard in the everyday sense. It would require overcoming conditions far outside normal engineering experience. So no, we are not going to dig to the center of Earth anytime soon. And perhaps that is part of the beauty of the topic. The deep Earth remains mostly unreachable, not because it is uninteresting, but because it is so physically immense and so materially hostile that it humbles every attempt to approach it directly. The planet keeps some of its structure hidden, not through secrecy, but through scale. Still, human curiosity has not given up just because direct travel is limited. When digging could not take us very far, science found other ways to listen. If the Earth would not open fully to drill bits, perhaps it could reveal itself indirectly. Perhaps its internal structure could be inferred from heat, rock samples, gravity, magnetism, and the way vibrations move through it. That realization changed the story. The question was no longer only how far down can we physically go, but how far down can we understand? And that is, in some ways, an even more beautiful question. Because the goal is not simply to arrive at the center like a traveler reaching a destination. It is to learn what kind of planet Earth actually is, why it has layers, why some regions are rocky and some metallic, why some parts move, why the surface breaks into plates, why the magnetic field exists, why the world above depends so much on places below that no person will ever stand inside. So the old image of digging straight down still has value, even if it is only a joke. It gives the mind a direction, downward, through the familiar surface and into the hidden depth. It reminds us that Earth is not just land and ocean spread across a globe, but a layered interior world with a history written in heat, separation, and slow change. And once that question settles in, another one rises quite naturally. If the deep Earth is too far, too hot, and too difficult to reach directly, then why is it layered the way it is in the first place? Why is there a crust at all? Why a mantle? Why a core? That answer begins not with digging, but with the early Earth, when the planet itself was younger, hotter, and still sorting its own materials into the hidden structure we live above now. In the beginning, Earth was not the quiet planet we know now. It was not a world of cooled crust, ocean basins, forests, roads, and sleeping cities. It was younger then, hotter then, and far less settled. The early Earth carried enormous heat from the violence of its formation, from constant impacts, from compression, and from the decay of radioactive elements inside it. For a time, the planet was not arranged into the calm, layered structure we describe today. It was still becoming itself. And that matters, because Earth's layers did not appear like stacked shelves already waiting inside the planet. They formed through a long process of separation. When Earth was young and much hotter, its materials were able to move more freely than they do in the rigid surface world we know now. Dense substances did not remain mixed evenly with lighter ones forever. Gravity slowly pulled the heavier materials inward, while lighter materials stayed higher. Over time, this sorting changed the entire structure of the planet. Iron was one of the most important materials in this early rearrangement. Because iron is dense, it tended to sink toward the center as the young Earth remained hot enough for large-scale internal separation. Other heavy elements moved inward as well, while lighter rocky materials stayed farther out. This process is called differentiation, but in simple terms, it means the planet began sorting itself by weight and composition. The deeper Earth became more metallic, the outer portions became rockier, and from that slow, powerful separation, the major layers of Earth began to emerge. This is why Earth is not the same all the way through. The crust, mantle, outer core, and inner core are not just convenient names humans made up to organize a diagram. They reflect real differences inside the planet. Different materials, different densities, different temperatures, different physical behavior. The Earth beneath us is layered because, early in its history, heat and gravity allowed matter to separate into regions that were no longer alike. There is something elegant about that. A planet begins in disorder, heat and collision, and over immense time it becomes structured. Not simple, but structured. The densest materials gather at the center. Rocky material forms the great middle regions. A thin outer shell cools enough to become the surface world where future oceans and continents can exist. The planet becomes organized, not because it is calm yet, but because physical forces continue acting on it without pause. And even though this major sorting happened long ago, the result is still with us now. We live on the outer expression of that ancient process. The crust beneath our feet exists because lighter rocky material remained near the outside. The deeper mantle reflects a vast interior of hot rock. The core exists because the densest materials moved inward. And far below us, the contrast between these layers still shapes the planet's behavior, from plate motion to internal heat flow, to the generation of the magnetic field. So when we ask why Earth has layers at all, the answer begins with a younger world that was much less stable than the one we know. It begins with a planet still hot enough to change itself from within. That early heat did more than make Earth uncomfortable or violent. It made separation possible. Without that heat, materials would not have moved and sorted in the same way. Without gravity, the heavy and light parts would not have been pulled into different regions. And without time, that structure would never have become so pronounced. Earth's interior is the result of all three working together: heat, gravity, time. The strange thing is that this layered structure feels obvious to us now, only because we are used to hearing about it. But if you pause for a moment, it is actually remarkable. We are living on the cooled edge of a planet that once sorted its own insides into hidden realms. A thin crust above a deep mantle, a metallic core below that, a solid center inside liquid metal, all of it shaped by processes that began before life, before oceans as we know them, before anything human could have stood here and wondered. And yet the old heat has never fully disappeared. Earth is cooler than it once was, but not cold inside. The layered world formed in the past is still active in the present. The structure remains, and the energy within it still matters. But before following that deeper motion, it helps to stay a little longer with the outer part of the story. Because the layer we actually live on, the crust itself, is much thinner than most people ever imagine. What feels broad and stable to us at the surface is, on planetary scale, astonishingly thin. That is one of the strangest perspective shifts in the whole story of Earth's layers. We live among mountains, plateaus, deserts, coastlines, canyons, forests, cities, and roads that seem large enough to define the world. A mountain range can feel immense. A deep valley can feel ancient and bottomless. Even a simple stretch of ground beneath a house can seem solid in a final sort of way, as though it continues downward in the same dependable form forever. But it does not. The crust, which is the outermost solid layer of Earth, is only a very thin outer shell compared to the full size of the planet. The Earth's radius is more than 6,000 kilometers, while the crust is only a small fraction of that depth. In some places it is thinner, in other places thicker, but in either case it is far less substantial than human instinct tends to imagine. On the scale of the whole planet, the crust is more like a skin than a great thick wall. And yet everything familiar to us happens there. Every field, every road, every tree root, every city block, every beach, every sleeping animal, every farm, every buried pipe, every train line, every quiet house at night exists on this thin outer layer. Human life unfolds entirely on the surface expression of a shell that is delicate in proportion to the world beneath it. We do not live in the deep earth. We live on its outer edge. That can be hard for the mind to hold at first, because surface experience is so convincing. When you stand on rock, it feels absolute. When you walk across pavement, it does not suggest thinness. When you look across a mountain, you do not usually think of it as resting on a narrow planetary skin above a mantle that extends vastly deeper below. But this is one of the gentle lessons of geology. Scale can make something seem immense at one level, and very slight at another. A continent is enormous to us. The crust that supports it is still thin relative to Earth as a whole. There is something humbling in that. The familiar world is not perched on a boundless block of sameness. It rests on a relatively narrow zone that formed as the outer part of a layered planet cooled. That crust is solid enough to support forests and buildings, yet thin enough that below it, the nature of Earth changes quite quickly. The deeper you go, the less the planet resembles the cool, rigid surface world we know. This does not mean the crust is fragile in the everyday sense. It is not like paper laid over emptiness. It is rock, dense and real, thick enough to contain mountain roots, mineral systems, and the long signatures of geological history. But relative to the full Earth, it remains a modest outer layer, not the main body of the planet, and it is not even the same everywhere. Some parts of the crust are thinner than others. Some regions are older. Some are younger. Some support continents. Others lie beneath the ocean floor. Even before we leave the crust entirely, we begin to see that Earth's outer shell is not one smooth, even wrapping around the globe. It is varied, broken, and shaped by a long history of creation, movement, and recycling. That is part of why the crust is such an important place to pause in this descent. It is easy to rush past it because it is the layer we already know best. It is the layer of ordinary experience. The layer of shoes on pavement, rain in soil, roots in dirt, and buildings set into stone. But in another sense, it is also the most surprising layer, because it teaches us how little of the planet we actually inhabit. We live on the cooled boundary of a much larger interior, a very thin margin between open air above and enormous depth below. And once that idea settles in, another detail starts to matter. The crust may be thin overall, but it is not uniform. The crust beneath the oceans is not quite like the crust beneath the continents. They differ in thickness, density, and character. And those differences help shape the surface world in ways that reach far beyond what we usually notice. So before we go deeper, it helps to stay with the crust just a little longer and ask a more specific question. What kind of crust are we actually standing on? The crust may be thin when compared to the whole Earth, but it is not all one kind of crust. That is an important detail, because once we begin looking more closely, the surface of the planet becomes more varied than it first appears. The ground beneath a continent is not built quite the same way as the ground beneath the open ocean. Both belong to Earth's outer shell, but they differ in thickness, density, age, and behavior. And those differences help shape the face of the planet we live on. Continental crust is generally thicker than oceanic crust. It is the crust that supports the continents, the great land masses where forests spread, cities rise, rivers cut valleys, and mountain ranges gather over long spans of time. Continental crust is made mostly of lighter rocky material, and because it is less dense, it tends to sit higher. That is part of why continents stand above sea level, rather than remaining submerged beneath the oceans. They are not simply random patches of dry land. They are built from crust with different physical properties. Oceanic crust, by contrast, is usually thinner and denser. It forms the outer rocky layer beneath the deep oceans, and it is made from darker, heavier material than much of the continental crust. Because it is denser, it tends to sit lower, which helps create the great basins where ocean water gathers. So from the beginning, the broad pattern of Earth's surface, continents rising higher, oceans resting lower, is tied to the fact that the crust itself is not the same everywhere. This difference also affects age. Much of the continental crust is very old. Some parts of it have survived for immense spans of geological time, holding traces of Earth's distant past. Oceanic crust, on the other hand, is often much younger. It is created more actively and destroyed more regularly. New oceanic crust forms at mid-ocean ridges, where material rises and cools, while older oceanic crust can eventually sink back into the Earth at subduction zones. So the ocean floor is not just lower ground. It is part of a more active cycle of renewal and recycling. That makes the seafloor more dynamic than many people imagine. When most people picture the ocean floor, they imagine a still, flat expanse hidden beneath dark water. But in geological terms, it is part of a moving system. New crust can form there. Old crust can be carried away. It can bend, sink, and return downward into the deeper Earth. Meanwhile, many continental regions preserve far older crust that has remained above for vast stretches of time, even while being reshaped at the surface by wind, water, ice, and life. So even within the crust, Earth already shows us two different ways of being. One is generally thicker, lighter, and longer lasting. The other is thinner, denser, and more actively recycled. One helps support the continents. The other underlies the oceans. Together, they create the uneven outer skin of the world, a surface not built as one continuous material, but as a varied shell with contrasting parts. There is something beautiful in that contrast. The oceans and continents do not sit where they do by accident alone. Their placement is related, in part, to the physical character of the crust beneath them. Land and seafloor are not merely decorations laid across the same base. They are expressions of deeper material differences that began long before human beings gave names to coastlines and continents. And those differences do not remain still. Because the crust is not one uniform covering, it does not move as one either. It is broken into great pieces, and those pieces include both oceanic and continental regions. They shift slowly over time, carrying land masses, opening oceans, closing seas, and building mountains through their motion. The uneven nature of the crust is part of what makes the surface world so active across geological time. So this is where the story begins to change again. The crust is not only thin, it is not only varied, it is also broken. The ground beneath us feels continuous when viewed from a road or a hillside or the floor of a room. But on the scale of the planet, Earth's outer shell is divided into giant moving plates. And once that idea enters the picture, the surface becomes harder to see as fixed at all. The ground feels continuous when we move across it. A road leads into another road. A field opens into a forest. A shoreline curves along a continent. Even mountain ranges, which rise and fold in dramatic ways, still seem connected to the land around them, as though Earth's outer shell were one single unbroken surface wrapping cleanly around the planet. From the perspective of ordinary life, that impression makes sense. The world beneath us appears still, whole, and settled. But the surface of Earth is not one smooth, unbroken shell. The outer rigid part of the planet, called the lithosphere, is broken into enormous pieces known as tectonic plates. These plates are not small fragments, and they are not cracks in the casual sense. They are vast sections of Earth's outer shell, large enough to carry continents, ocean floors, and entire regions of the planet with them. They fit together across the globe in a pattern that is slow, restless, and always in motion, even when that motion is too gradual for human senses to notice. This means that the ground beneath us is part of something larger than a local landscape. A continent is not only land, it is part of a plate, or part of several plates, moving across geological time. The floor of the ocean is not just a basin holding water. It too belongs to plates, and those plates shift, separate, and meet in different ways. Oceanic crust and continental crust can both be carried along within this broken outer system. So the Earth's surface is not divided neatly into land on one hand and sea on the other. It is divided into moving plates that may contain both. That is one of the reasons the planet's surface has changed so much over deep time. Continents have not always sat where they do now. Oceans have opened and closed. Shorelines have changed. Land masses have come together and drifted apart. The world map feels permanent only because human lives are short. On the timescale of the planet, the surface is more like a long, slow rearrangement. These plates do not race. They move gradually, often at speeds similar to the growth of fingernails. That slowness is important to picture. Earth is not jerking its continents from place to place. It is shifting them patiently, so slowly that a human lifetime can pass without the movement being visible in any ordinary sense. And yet, over millions of years, that gentle motion becomes enough to build oceans, raise mountains, and reshape the surface of the world. Most of the action happens where plates meet. At some boundaries, plates move apart. When that happens, material from deeper below can rise, cool, and help form new crust. At other boundaries, plates move toward one another. One plate may sink beneath another, or two thick continental masses may press together and crumple upward. In other places, plates slide sideways past each other, creating tension that can build quietly and then release. So even though the plates move slowly overall, the places where they meet can become zones of pressure, friction, heat, and change. This is why so many of Earth's most dramatic surface events happen near plate boundaries. Earthquakes often occur where stress builds between moving plates. Volcanoes are common in regions where plates separate or where one plate sinks beneath another and helps generate molten material. Mountain ranges can rise where continents collide and push rock upward over immense spans of time. Many of the features humans find most powerful or destructive at the surface are connected, in one way or another, to the fact that Earth's rigid outer shell is broken and mobile. And yet, even this mobility is quiet most of the time. The plates do not announce their motion every day. A person can spend a whole life in one place and feel as though the land beneath them has always been as it is. That feeling is understandable. The scale of the motion is simply too large in time and too slow in pace for the body to register directly. But the stillness is only apparent. Beneath the calm of roads, forests, neighborhoods, coastlines, and sleeping towns. The broken surface of Earth is participating in a much longer movement. There is something strangely comforting in that idea. The planet is not broken in the sense of being ruined. It is broken in the sense of being structured into pieces that allow change. The surface is not fixed because Earth is not finished. Its outer shell shifts, meets, presses, and pulls apart, slowly writing the long history of the world in stone: ocean basins, trenches, faults, and mountains. And once that becomes clear, another question naturally begins to rise. If the solid surface of Earth is divided into these massive plates, and if those plates are truly moving at all, then what is pushing them? What is patient enough, deep enough, and powerful enough to make the ground itself drift so slowly over time? The surface of Earth does not move by itself. The plates are real, and their slow motion is real. But they are not wandering without cause. Something deeper is involved. Something older than continents in their present form. Something patient enough to work over spans of time so long that coastlines can open, mountains can rise, and oceans can be born without the movement ever feeling hurried. To understand why the surface moves, we have to look below it, into the long memory of heat inside the planet. Earth still carries heat from its early formation. When the planet first came together, that process involved collisions, compression, and intense internal energy. Much of that early heat has been lost over time, but not all of it. The Earth today is cooler at the surface than it once was, yet deep inside it remains warm to extremely hot. The planet is not a cold stone covered by a thin layer of life. It is a world still releasing internal heat outward, slowly and continuously. There is another source of heat as well. Inside Earth, certain radioactive elements naturally decay, and that decay releases energy. It is a quiet process, invisible in ordinary life, but over geological time it matters. This internal production of heat helps keep the planet active from within. So the heat inside Earth is not only a leftover from the distant past. Part of it is still being generated even now. That hidden warmth is one of the reasons the planet's interior does not simply become motionless. Heat creates differences. It makes some regions more energetic than others. It encourages movement over long spans of time. In Earth's deep interior, especially within the mantle, heat helps drive slow shifting and circulation. This motion is not fast, and it is not chaotic in the everyday sense. It is gradual and vast, unfolding in a medium that does not behave like water or air, but still changes shape across immense time. The plates above are linked to that deeper motion. This is the key idea. The moving surface is not an isolated outer phenomenon. The crust and uppermost rigid part of the planet are tied to what is happening below. The rigid plates ride above deeper regions that are hotter and more able to deform. So when we speak about plate motion, we are really speaking about a whole planet system. The surface does not drift on its own. It is connected to internal energy rising from below and to the slow behavior of deeper rock inside the Earth. That changes the way the surface should be imagined. A continent is not simply sitting on a fixed foundation forever. An ocean floor is not resting on a perfectly still base. Instead, the outer shell of Earth is part of a broader living structure. not living in the biological sense, but active in the geological one. It responds to heat, time, and depth. What appears settled from a human viewpoint is, in the language of the planet, still in motion. This can be hard to feel because human time is so short. A plate may move only a small amount in a single year. Nothing about that motion feels dramatic while making breakfast, driving to work, or lying in bed at night. The land outside your window does not appear to drift. The floor beneath your feet does not seem to carry you anywhere. But geological time changes the meaning of stillness. Over millions of years, a motion that is nearly invisible in one day becomes enough to rearrange the face of the world. So the true answer to why the surface moves is not a sudden push or a single mechanism acting in isolation. It is the result of heat within the earth, some ancient and some still being produced, slowly working through the mantle and influencing the rigid shell above. The movement is slow because the planet is slow. The force is quiet because deep time is quiet. Yet the consequences are enormous. And this is where the story becomes stranger. To follow the cause of surface motion any farther, we have to go below the crust and into the mantle itself. Not into empty space, and not into a simple underground ocean of molten rock, but into a vast region of hot stone that behaves in ways unlike the stone we know at the surface. Because the mantle is where one of Earth's most beautiful paradoxes begins. It is solid, and yet, somehow, it moves. Below the crust lies the mantle, and this is where the Earth begins to feel much less familiar. When people first imagine the inside of the planet, they often picture a hollow space, or perhaps a giant underground sea of molten rock stretching endlessly beneath the surface. It is an understandable image. Once the thin outer shell is gone, the mind wants to replace it with something dramatic and simple. A glowing interior, a fiery chamber, a world of liquid heat below the rock we stand on. But the mantle is stranger than that, and calmer too. It is not empty space. It is not a single underground ocean of lava. It is a vast layer of hot rock, extending far deeper than the crust, and making up most of Earth's volume. If the crust is the narrow outer skin of the planet, then the mantle is the enormous body beneath it, thick, heavy, mineral-rich, and central to almost everything the Earth does over long periods of time. This is the great middle region of the planet. It begins below the crust and continues downward for thousands of kilometers. That depth is hard to hold in ordinary thought. We are used to thinking in roads, hills, buildings, and weather. Even mountains, which seem so large at the surface, are small compared to the scale of the mantle. The mantle is not a local underground layer. It is a planetary one, wrapping deep around the core and forming most of the Earth's bulk. It is made mostly of silicate rock, rich in elements like oxygen, silicon, magnesium, and iron. That description may sound technical at first, but what matters most here is the feeling of it. The mantle is rocky, not metallic like the core, and not light or fragile like the world of air above us. It is dense, mineral-heavy, and held under conditions far beyond anything found at the surface. The deeper it goes, the greater the heat and pressure become, and those conditions change the way rock behaves. This is where ordinary intuition begins to struggle. At the surface, rock feels final. It feels like the definition of stillness. Stone walls, cliffs, sidewalks, mountain faces. These are some of the clearest symbols of solidity we know. So it is natural to imagine the mantle as a rigid mass sitting motionless forever beneath the crust. But the mantle is not simply a larger version of surface rock. It is hot enough, deep enough, and pressured enough to behave differently across long spans of time. That does not mean it is liquid in the everyday sense. This is important because the mantle is often misunderstood as fully molten. In reality, most of it is solid rock. Not cool rock, not comfortable rock, but solid rock nonetheless. Yet that solidity exists under such extreme conditions that the mantle can slowly deform, bend, and shift over immense timescales. It is not a sea, but neither is it frozen in absolute stillness. So the mantle occupies a strange middle ground in the imagination. It is solid, but not stubborn in the way surface stone is stubborn. It is deep, hot, and capable of movement so slow that it escapes ordinary notice. Much of Earth's long internal motion depends on what happens here. The mantle helps transfer heat upward. It helps influence the movement of tectonic plates above. It is one of the main reasons the surface of the planet is not fixed forever in one arrangement. In that sense, the mantle is one of the quiet engines of the Earth. Not an engine of noise or sudden force, but one of patience. It works over spans of time so long that continents can drift, oceans can widen, mountains can rise, and the surface can be reshaped without any single moment announcing the full story. The mantle does not hurry. It simply continues deep below, changing the world above it through motions almost too slow to imagine. There is something especially sleep-friendly about that image. A vast, hidden layer of hot rock, stretching downward far beyond the crust, not collapsing into chaos, not bursting constantly into flame, but holding and transferring energy in a patient planetary rhythm. The Earth below us is not hollow and not simple. It is structured, heavy, and active in ways that are easy to miss because they unfold beneath the pace of human life. And that brings us to the mantle's quiet paradox. If it is made mostly of solid rock, then how can it move at all? How can something be solid and yet still slowly flow enough to influence the surface of an entire planet? That question sounds impossible at first. How can rock be solid and still move? In ordinary life, the two ideas seem to cancel each other out. We think of solid things as fixed. A stone does not pour. A cliff does not drift. A wall does not slowly reshape itself in the night. Solid seems to mean firm, still, and resistant to change. So when we hear that the mantle is made mostly of solid rock, but that it also moves over time, it can sound like a contradiction. But the contradiction begins to soften once time enters the picture. A material does not have to behave the same way on every timescale. Something can resist motion in the short term and still change in the long term if the conditions are extreme enough. This is one of the most important ideas for understanding the deep Earth. At the surface, rock responds to human time. It feels rigid because our lives are short, our forces are small, and our observations are brief. But deep in the mantle, rock exists under enormous heat and pressure for spans of time so vast that its behavior begins to look different. It is still solid, but it is not eternally locked in one exact shape. Under those deep conditions, mantle rock can slowly deform. It can be pressed, stretched, and made to yield without turning into a normal liquid. That distinction matters. The mantle does not slosh like water in a basin. It does not ripple like soup or splash like a wave. Its motion is far slower and far more restrained than that. Yet over immense stretches of time, the rock can creep. It can shift little by little, enough for material inside the earth to move and for heat to be carried through the planet. So the answer is not that solid rock suddenly becomes something else. The answer is that solidity itself becomes more subtle when a planet is involved. This happens because the deep mantle is not just hot. It is hot while also being compressed under extraordinary pressure. That combination changes how minerals respond to stress. The rock remains solid overall, but it can deform in ways that are almost impossible to notice unless the span of time is enormous. What appears fixed on a human scale becomes flexible on a geological one. There is something strangely calming in that idea. The deepest motions of Earth are not always dramatic. They do not require constant melting or violent upheaval. Sometimes they happen because a solid material, given enough heat, pressure, and time, can slowly change shape without losing its identity. The mantle keeps its rocky character, and still it yields. It remains solid, and still it participates in motion. This helps explain how Earth can be both stable and active at once. The ground under a town can feel dependable. A mountain can appear permanent. A coastline can seem ancient and settled. Yet below all of that, the mantle is participating in a quieter kind of movement. One that does not break the meaning of solidity, but stretches it across a much larger scale. Solid in the deep earth does not mean forever motionless. It means structured, dense, and cohesive, while still capable of gradual change. That is why time is such an important part of the story. A day reveals nothing. A year reveals almost nothing. Even a lifetime reveals very little of the mantle's motion directly. But millions of years allow a different picture to emerge. Over those spans, rock that once seemed fixed can move enough to help carry heat upward, influence plate motion, and participate in the slow internal circulation of the planet. Time changes what movement looks like. It also changes what stillness means. So the mantle is not a rigid block beneath the crust, and it is not a molten sea either. It is something more patient than either of those images. A vast body of hot rock that holds together and yet can slowly deform. A layer that does not rush, but does not remain unchanged. A deep region where the ordinary meanings of hard and soft, fixed and flowing, begin to blur. And once that becomes easier to picture, another image starts to form. If rock in the mantle can yield so slowly over immense time, then its motion is not random. It becomes part of a larger pattern. Heat rises, cooler material sinks, energy moves outward from the deep earth in a broad and patient circulation. So from this quiet yielding of solid rock, a greater motion begins to appear. The mantle does not merely shift, it slowly stirs. The mantle does not move in every direction at once without pattern. Its motion is slow, but not meaningless. Once we accept that the deep rock of the mantle can yield over immense spans of time, a larger image begins to take shape. the Earth is not simply warm inside. It is slowly transferring that internal heat outward. And one of the ways it does this is through broad, patient circulation within the mantle itself. This circulation is often compared to stirring, though it is far quieter and far slower than anything that word suggests in ordinary life. Nothing churns quickly, nothing splashes. There are no visible currents as there are in rivers or clouds. Instead, the deep earth moves with almost unimaginable patience. Heat from lower regions influences the material above it. Hotter mantle material can become more buoyant relative to cooler surroundings, and over time, that difference encourages upward motion. Cooler material in other regions can sink downward. So the mantle participates in a long, slow exchange, not with the urgency of weather, but with the still persistence of a planet working through its own stored energy. This is one of the hidden rhythms beneath the surface world. The Earth below us is not only layered, it is active in the sense that energy continues moving through it. Heat does not remain trapped forever in the deepest interior. It gradually travels outward, and the mantle plays a major role in carrying that energy along. In that sense, the mantle is not simply a thick layer of hot rock sitting between crust and core. It is part of an ongoing planetary process. That process matters at the surface even if we do not directly feel it. The slow circulation of the mantle is one of the deep causes behind tectonic motion. The plates above do not move in isolation. They are connected to what happens in the hot, deforming rock below. That does not mean every plate is pushed or pulled in one simple way by a single mantle current. The full system is more complex than that. But the general truth remains. Heat-driven motion in the mantle is part of the larger system that helps keep Earth's surface from becoming permanently still. So the world above is linked to a hidden movement below. A coastline, a volcano, an earthquake zone, a mountain range. These surface features and events are not only local accidents. They are connected in part to deep flows of energy and material that the human eye never sees directly. What looks fixed from above is influenced by circulation far beneath the crust. The surface is not separate from the interior. It is the upper expression of processes still unfolding in the dark. There is something beautiful about the pace of that movement. The mantle does not rush to deliver heat. It does not seek balance in a moment. It carries energy on timescales so long that continents can drift, while the process continues quietly underneath them. That slowness is part of what makes Earth feel stable to us. The change is real, but it is stretched across such vast spans of time that human life catches only the still frames. A road, a city, a shoreline, a hillside, all seem settled because the deeper motion unfolds beneath the speed of ordinary awareness. And yet the motion is enough. Enough to help reshape oceans. Enough to influence plate boundaries. Enough to participate in the long tectonic life of the planet. Earth remains geologically active not because it is violent every day, but because it still holds heat and still has ways of moving that heat outward. The mantle's slow stirring is one of those ways. Even so, the mantle should not be imagined as perfectly uniform from top to bottom. That would be too simple. Just as the crust differs from place to place, the mantle also changes with depth. Pressure rises. Mineral structures shift. Certain boundaries inside the mantle mark transitions where the same broad rocky material begins behaving somewhat differently. The deeper the descent, the less helpful simple surface language becomes. We are no longer dealing only with rock, but with rock transformed by conditions that keep intensifying. So the mantle has its own hidden structure too, its own thresholds, its own internal changes, its own deeper complexity waiting below the broad image of slow circulation. And that means the next step in our descent is not downward into an entirely new layer just yet, but deeper into the mantle itself. Because even here, within this vast middle region of the Earth, the story continues to change. The mantle is often introduced as though it were one enormous, continuous region of hot rock. That is useful at first. It gives the mind a broad shape to hold. The crust is thin above. The mantle is vast below. Heat moves through it. Rock deforms slowly within it. All of that is true. But as the descent continues, the picture becomes more detailed. The mantle is not perfectly uniform from top to bottom. It changes with depth, and those changes matter. Pressure is one of the main reasons why. The deeper you go inside Earth, the more weight there is above. That growing pressure affects the minerals in the mantle, not by turning them into something unrelated, but by changing how their atoms are arranged. A mineral can keep the same overall chemistry, and yet take on a different internal structure under more extreme conditions. In other words, the rock is still broadly rock, but the form it takes is not exactly the same at every depth. This is one of the quieter surprises of the deep Earth. We tend to think of materials in simple categories. Stone is stone, metal is metal, water is water. But under planetary conditions, those categories begin to stretch. The mantle is not just a single endless mass of identical substance. It contains transitions, thresholds, and internal boundaries where the behavior of the material changes because the conditions have changed. Depth itself reshapes the meaning of the rock. So even within this great middle layer, Earth remains layered. There are regions in the mantle where mineral structures shift in response to increasing pressure and temperature. These transitions do not always create a dramatic visual boundary, at least not in the way a cliff edge separates land from air. They are hidden transitions deep within the planet, where one arrangement becomes another. Yet these changes matter because they influence how material moves, how heat is transferred, and how vibrations pass through the Earth. That last detail is especially important. Much of what we know about Earth's deep interior comes from seismic waves, and those waves do not move through every part of the mantle in the same way. Their speed and path can change depending on the material they pass through. So when scientists detect changes in how waves travel at certain depths, those changes can reveal internal boundaries in the mantle itself. The Earth does not open for direct viewing, but it does leave patterns in motion, and those patterns tell us that the mantle is more structured than a simple first glance suggests. This means the mantle is not only a place of circulation, it is also a place of transition, a place where increasing depth brings new mineral forms, new physical behavior, and new complexity. The broad image of slow stirring remains true, but now it becomes richer. The material doing that stirring is not identical from top to bottom. Earth's interior keeps changing as the descent continues, layer within layer, threshold within threshold. There is something almost humbling in how quickly simple words begin to fail. At the surface, everyday language works well enough. Stone, dirt, metal, water, heat. But deeper inside the planet, those words begin to lose some of their clarity. Rock remains rock, but not in a way the surface fully prepares us for. The deeper Earth is still made of matter, still governed by physical law, and yet it enters conditions so extreme that familiar descriptions become less satisfying. The planet asks for a calmer, more patient kind of imagination. And that is part of what makes this descent so beautiful. The deeper we go, the less Earth resembles a simple globe with a thin shell and a hot middle. It becomes a world of gradients, transitions, and hidden structure. Even the mantle, which once seemed like one great region between crust and core, reveals its own internal story. Pressure reshapes minerals. Boundaries appear where none would be obvious from above. The planet is not just deep, it is intricately deep. But this intricacy does not go on forever in the same material. Eventually, the rocky world of the mantle gives way to something more metallic. The character of Earth changes again. The great mineral-rich interior above is left behind, and a new boundary approaches, one of the most important in the whole planet. Below the mantle, Earth does not simply continue as hotter rock, it begins to enter the realm of the core. Far below the deepest part of the mantle, the Earth changes character again. This is not a small change, and not merely a continuation of what came before. It is one of the sharpest hidden transitions in the entire planet. For thousands of kilometers, the descent has carried us through rocky regions, through the vast mineral world of the mantle, through pressure-driven transitions and slow-moving solid stone. But eventually, that rocky domain reaches its limit. Beyond it lies the edge of the core. This boundary marks a major change in what the Earth is made of. Above it, the planet is dominated by rocky material. Hot rock, pressured rock, slowly deforming rock, but rock nonetheless. Below it, iron-rich metal becomes central. The Earth does not become empty or chaotic at this depth. It becomes more metallic. The composition shifts, and with that shift, the very nature of the deep interior begins to feel different. What was once a vast world of silicate minerals gives way to a darker and denser realm where metal takes over. That transition is one of the reasons this boundary matters so much. It is not only a dividing line between two regions, it is a place where two very different parts of the planet meet. Above, the mantle continues its slow movement of hot rocky material. Below, the core begins, with its metal-rich composition and its own deep internal behavior. This meeting point helps scientists understand how Earth's layers interact, because the planet is not a set of isolated compartments. Heat moves through it. Pressure shapes it. Boundaries influence what can pass, what can change, and how energy is transferred from one region to another. The conditions here are immense. By the time we reach the edge of the core, both temperature and pressure have risen to levels far beyond anything known at the surface. The rock above is already under extraordinary strain. The metal below exists under conditions so extreme that everyday language starts to feel very small. There is no direct human image for this place. No cave, no furnace, no ocean trench. No mountain interior offers a true comparison. The scale is too large, the depth too great, the conditions too unlike the upper world where human life unfolds. And yet this hidden boundary is real. It exists whether or not we can picture it clearly. It exists beneath continents, beneath oceans, beneath sleeping forests and midnight cities and long, quiet roads. Far below everything familiar, the mantle and core meet in darkness. The listener does not have to imagine it in detail to feel its significance. It is enough to understand that the earth is not merely deep, but divided into realms whose materials and behaviors differ in profound ways. There is something almost ceremonial about crossing this threshold in thought. The mantle has already taught us that the deep earth is stranger than surface intuition suggests. Rock can remain solid and still move slowly. Pressure can change the form of minerals. Hidden boundaries can shape the motion of waves and the transfer of heat. But the edge of the core goes further. It tells us that the earth below is not just rock becoming hotter and deeper forever. At some point, the story changes. The planet enters a more metallic world. This region is also important because it helps reveal how the layers influence one another. The core does not exist separately from the mantle above it. Heat passes outward. Material behavior in one layer affects motion in another. The Earth's interior is a connected system, and the edge of the core is one of the most important places where that connection can be studied indirectly. It is a hidden border, but not a sealed one. The planet remains one body, even while its internal parts differ so dramatically. That is part of what makes this boundary so beautiful. It is hidden, unreachable, and yet central to the life of the whole Earth. The surface above depends on processes that trace back through the mantle and toward the core. The deeper we go, the clearer it becomes that the Earth is not a simple globe with a quiet outside and a hot inside. It is layered, structured, and full of thresholds where the meaning of matter changes. And now, beyond this great boundary, the descent enters one of the strangest regions of all. Not a cave, not a chamber, not a hollow space, but a dark metallic ocean surrounding the deeper center of the planet, moving in silence where no human eye will ever look directly. Beyond the boundary of the mantle lies the outer core, and here the Earth becomes stranger still. This is not a chamber in the ordinary sense, and not an empty region waiting beneath the rock above. It is a vast layer of liquid metal deep inside the planet, surrounding the solid center like a dark hidden sea. No human being has ever seen it directly. No machine has come close to entering it, and yet this unseen layer is one of the most important parts of Earth. The outer core is made mostly of iron, along with nickel and a smaller amount of lighter elements mixed in. That composition matters because it marks such a strong change from the rocky mantle above. For thousands of kilometers, the descent moved through silicate-rich rock, however strange that rock became under heat and pressure. But in the outer core, metal dominates. The Earth is no longer mostly rocky here. It is iron-rich, dense, and fluid in a way the mantle is not. What makes this especially remarkable is that the outer core is liquid. At first, that may sound surprising. This region is incredibly deep, and the pressure there is immense. It would be reasonable to imagine that everything at such depths must be compressed into solidity. But temperature matters too. The outer core is so intensely hot that, under those conditions, This metallic layer remains liquid rather than solid. The balance of heat, pressure, and material composition creates a region that does not behave like the rocky mantle above it and does not yet become the solid center below. So the outer core occupies a strange middle position in the Earth. It lies beneath the mantle and surrounds the inner core. Above it is the vast world of hot, slowly deforming rock. Below it is the compressed metallic center. Between the two is this enormous layer of liquid metal, hidden in darkness, moving far below the surface of every ocean, continent, forest, city, and sleeping home. There is something powerful in simply trying to picture that. Not flames, not open caverns, not a glowing underground sky. Just a deep metallic layer, hot enough to remain liquid, wrapped around the center of the planet, existing in silence beyond all direct human reach. The farther inward the journey goes, the more the Earth feels less like a place and more like a process. A layered structure still shaped by temperature, density, and motion. And the outer core does not merely exist. It moves. That motion is not random sloshing. It is part of Earth's internal dynamics, tied to heat flow, rotation, and the behavior of the liquid metal itself. The outer core is active, though active on a scale and in a setting no human body could ever experience directly. Its motion belongs to the deeper workings of the planet, to the long hidden systems that help connect the center of Earth to the world above. This is one of the reasons the deep Earth matters so much to life at the surface. It would be easy to assume that such a remote layer has little to do with everyday existence. After all, the outer core is unimaginably far below roads, coastlines, trees, clouds, birds, and human routines. But the Earth is not built in disconnected pieces. The deeper layers influence the outer ones, and the outer core is one of the clearest examples of that truth. Something happening far below the crust can still matter to the conditions of the surface world. That is part of what gives this section of the planet such quiet importance. It is hidden, unreachable, and yet not irrelevant. The outer core helps remind us that the world we know is supported by processes we never directly witness. Under the familiar surface lies not only rock and heat, but moving liquid metal, deep enough to feel almost mythical, and real enough to be essential. So in one sense, the outer core is a place of darkness, but in another sense, it is a place of consequence. Because this moving metal does more than remain hidden at depth. It helps generate something that rises far beyond the deep Earth itself, extending outward around the whole planet. An invisible field, a planetary presence in space, a structure surrounding Earth that begins in part with motion in this unseen metallic sea below our feet. The magnetic field around Earth does not begin in the sky. It can feel that way from the surface. Compasses point across open air. Auroras shimmer high above the poles. Space itself seems like the natural home of magnetism, as though the field surrounding Earth belongs mainly to the heavens. But the deeper truth is quieter and more surprising. Earth's magnetic field is tied, in large part, to motion happening far below the surface, in the liquid metal of the outer core. This means that something hidden beneath our feet helps create something extending far beyond the planet. That connection is one of the most beautiful in the whole story of Earth's layers. A process unfolding in darkness, thousands of kilometers below the crust, contributes to an invisible structure that surrounds the world. The field is not a separate ornament floating in space. It is linked to the inner life of the Earth itself. The basic idea is sometimes called the geodynamo. The word sounds technical, but the image behind it is gentle enough to hold. In the outer core, liquid iron moves under extreme conditions. That movement, shaped by heat, flow, and Earth's rotation, helps generate electric currents. Those currents in turn help produce the magnetic field. So the field is not simply there by default. It is part of an ongoing planetary process, something maintained by motion within the deep Earth. In that sense, the magnetic field is a kind of expression of hidden activity. It tells us that the Earth below is not silent in the absolute sense. Not noisy, not hurried, not chaotic, but active. The moving outer core does not stay sealed off from the rest of existence. Its motion reaches outward, into a field that extends beyond the atmosphere and into the space surrounding the planet. This is where the deep interior begins to feel less distant. Up to this point, the journey downward has moved through layers that seem remote from daily life. Thin crust, vast mantle, hidden transitions, liquid metal, all of it real, but easy to place far away in thought. The magnetic field changes that feeling. It reveals that the unseen Earth below is not just interesting in itself. It is involved in shaping the world above. A hidden process beneath roads, forests, oceans, and sleeping towns contributes to something that surrounds the entire globe. And that invisible field is not empty symbolism. It interacts with charged particles arriving from the sun. Space is not a perfect stillness. It is crossed by flows of energy and matter, and Earth exists within that wider environment. The magnetic field helps shape how the planet meets those incoming particles. So again, what begins below the crust does not remain below the crust. The interior and the exterior are connected. The deep Earth and near-Earth space belong to one larger story. Without this field, the world around Earth would be very different. That does not mean the planet would vanish or instantly become unrecognizable. But the conditions around it and the way it interacts with solar particles would not be the same. The magnetic field is part of what gives Earth its particular relationship to space. It helps define the invisible environment surrounding the planet, and that environment matters. There is something wonderfully humbling in that. A person standing in a quiet driveway at night or lying half awake under a blanket would never feel the outer core moving below. The magnetic field does not brush against the skin like wind. It does not glow in ordinary places. It does not announce itself. And yet it is there, an unseen planetary presence, shaped in part by the motion of liquid metal deep inside Earth. That is one of the soft marvels of geology and planetary science. The Earth is not simply layered downward, it also reaches outward. Its hidden interior contributes to structures far beyond the surface. The journey inward has led unexpectedly to something surrounding the whole world. What seemed buried and remote turns out to have consequences that extend into space itself. And once that is understood, another question naturally begins to rise. If this invisible field surrounds the Earth, what does it actually do for the world above? What does it mean, in practical and planetary terms, for Earth to carry this hidden magnetic presence around itself? Because the field is not only there, it also protects. The magnetic field does not sit around Earth doing nothing. It shapes a protective region around the planet, and that protection is one of the quiet reasons life at the surface has been able to unfold under the conditions we know. The field itself is invisible, but its effects reach far beyond the deep Earth where it begins. It helps shape the magnetosphere, a broad magnetic environment around Earth that interacts with the charged particles streaming outward from the sun. That solar flow is often called the solar wind, though it is not wind in the ordinary sense. It is a flow of charged particles moving through space, and Earth exists within its path. If the planet had no magnetic field, those particles would meet Earth very differently. But because the field extends outward into space, many of those charged particles are deflected, redirected, or guided around the planet, rather than simply arriving unchecked. In that way, the magnetic field helps create a kind of invisible shielding around the world. This protection is not absolute, and it is not a hard shell. The magnetosphere is not a wall. It is better understood as a dynamic region shaped by the relationship between Earth's magnetic field and the solar wind. It bends, responds, and changes with space weather conditions. Even so, its presence matters greatly. It helps reduce how directly the solar wind interacts with the planet, and that has been important for Earth's long-term environment. So once again, something that begins deep below our feet reaches far beyond the atmosphere. That is one of the most beautiful reversals in this story. We began with the ground, with crust and rock and hidden depth. We moved downward through the mantle and into the metallic core. And now, from the motion of liquid iron, we arrive at a protective magnetic region extending outward into space. The deep Earth and the high space around Earth are connected through one continuous planetary process. Some of the incoming particles do still make their way inward, especially near the polar regions. There, the magnetic field can guide charged particles down into the upper atmosphere, where they interact with gases and help create auroras. The northern and southern lights are among the most beautiful signs of this hidden relationship. They are not only lights in the sky, they are evidence that Earth is in conversation with space, and that the magnetic field helps shape how that conversation unfolds. So the aurora is, in a sense, a visible trace of an invisible shield. That shield does not usually announce itself in daily life. Most people do not walk outside thinking about the magnetosphere. They think about weather, traffic, light, noise, temperature, sleep. But the fact remains that Earth carries this magnetic protection around itself at all times, and that protection is tied back to the deep interior of the planet. The outer core moves. The magnetic field is generated. The magnetosphere takes shape. And life continues at the surface, often without noticing the hidden chain beneath it. That hidden chain is part of what makes Earth habitable in the particular way it is. Habitability depends on many things, of course. Distance from the sun, water, atmosphere, temperature, chemistry, time. But part of Earth's story also includes this magnetic protection, this deep-to-space connection that helps shape the planet's relationship with its environment beyond the atmosphere. The Earth is not protected only by what surrounds it from above. It is also protected by what rises outward from below. There is something deeply calming in that idea. The planet is not passive. It is participating in its own protection. Quietly, continuously. A hidden metallic motion in darkness contributes to an invisible field around the world, and that field helps shape conditions for everything living on the thin crust above. Forests, coastlines, birds, sleeping cities, quiet houses, open oceans, all of them exist on the outer edge of a system that extends from the deep core to the space around Earth. And if so much depends on what happens far below, then it is natural for the mind to keep following the descent. Because beyond the liquid outer core, still deeper inside the planet, lies the very center of Earth itself. And there, at the deepest point of all, another quiet paradox is waiting. The center is solid. At the deepest center of Earth, surrounded by a vast layer of liquid metal, lies a solid sphere. It is one of the quietest contradictions in the whole planet. By the time the descent reaches the center, the heat is extraordinary, far beyond anything the surface world can prepare us for. It would seem natural to imagine that the very middle of Earth must be molten, or even more fluid than the outer core around it. But the truth is stranger. The inner core is solid. Like the outer core, it is made mostly of iron and nickel. So in composition, these two deep regions are related. Both belong to the metallic heart of the planet, but they do not behave the same way. The outer core remains liquid, while the inner core is compressed into solidity. The difference is not because the center is cooler. It is because the pressure there is so immense that it changes what the metal can do. This is what makes the inner core such a beautiful paradox. It is unimaginably hot, and yet it stays solid because it is also unimaginably compressed. The weight of the whole planet pressing inward creates conditions so extreme that the iron at the center cannot remain liquid in the same way it does in the outer core. Heat pushes one way, pressure pushes another. At the center of Earth, pressure wins. So the deepest part of the planet is not hollow, and it is not molten all the way through. It is a solid metallic center, enclosed by a moving ocean of liquid metal. That structure is part of what gives Earth its hidden elegance. A thin crust at the surface, a vast rocky mantle beneath, a liquid outer core below that, and then, at the very center, a solid inner core under crushing force. The planet is not simple in its depth. It is layered with almost architectural precision, as though each deeper region reveals a new answer to the question of what matter becomes under greater heat, pressure, and time. The inner core is smaller than the outer core, but it is still immensely important. Not because it is large in comparison to the whole Earth, but because it belongs to the deepest structural reality of the planet. It is the central anchor of Earth's metallic interior, a region that tells us just how far conditions can depart from anything familiar at the surface. The ground beneath us may feel cool, ordinary, and complete. Yet all the way at the center, the planet remains under such intense force that metal is held in a state that seems to contradict the heat surrounding it. There is something calming in the image of that center. Not calming because it is gentle, but because it is so settled. After descending through changing layers, moving plates, slowly flowing rock, hidden boundaries, and a deep metallic sea, the journey arrives at a compressed stillness. the outer core moves. The mantle circulates. The plates drift. But at the very center, there is solidity once more. Not the light solidity of a stone in the hand, but the immense, pressured solidity of the Earth's deepest point. And yet, even here, the mystery does not end. Because no one has ever gone there. No machine has approached it. No person has seen the inner core directly. Everything we say about it comes from evidence gathered at a distance, from the way Earth behaves, from the way waves move through it, from the way the planet reveals itself without opening. That may be one of the most remarkable parts of the story. We know something about the deepest center of the Earth, and we know it without ever touching it. So the inner core becomes more than just the last layer in the descent. It becomes a reminder that the Earth can be deeply hidden and still understood, at least in part. The planet does not offer its structure to us through direct access. It offers clues, patterns, signals. It lets itself be studied indirectly through patience and inference rather than arrival. And that naturally raises the next question. If the deepest center of Earth is beyond all direct human reach, then how could we possibly know it is there? How do we know the outer core is liquid, the inner core is solid, and the layers exist as they do, when no one has ever traveled down to see them for themselves? The answer does not begin with digging any farther. It begins with listening. We know the deep Earth not because we have reached it, but because the planet speaks in waves. That shift matters. For much of this journey, the imagination has moved downward as though following a descent through crust, mantle, outer core, and inner core. It is natural to picture knowledge the same way, as though understanding must come from physically going there. But for the deep Earth, that is not how the story unfolds. We do not know its hidden structure through direct travel. We know it through signals. One of the most important of those signals begins with earthquakes. When the Earth shakes, energy travels outward through the planet in the form of seismic waves. These waves move through the crust, through the mantle, and toward the deeper layers below. They do not simply spread across the surface like ripples on water. They pass through the body of the Earth itself. In that sense, every significant earthquake sends a kind of message through the planet, a message that can be detected far away, and those messages change depending on what they pass through. That is the key. Seismic waves do not travel the same way in every material. Their speed can change. Their direction can bend. Some can pass through solids and liquids, while others cannot move through liquids at all. So if a wave behaves differently at a certain depth, or disappears from a certain path, that change becomes a clue. It suggests that the material inside Earth is not the same all the way through. It reveals that boundaries exist, even if no one will ever stand there to point at them directly. This is how the hidden Earth began to take shape in scientific understanding. Not through drilling to the core, not through opening the planet like a shell, but through careful measurement. Instruments placed around the world record how and when seismic waves arrive. Scientists compare those arrival times, paths, absences, and changes in speed. From those patterns, they infer structure. They reconstruct the unseen. The Earth, in a sense, has been mapped from the way it trembles. There is something deeply beautiful in that. A planet can remain closed to direct travel and still become knowable. Not fully, not perfectly, but meaningfully. The deep earth does not reveal itself through sight. It reveals itself through response. Strike the system, and the waves carry information. Listen carefully enough, and the interior begins to appear, layer by layer, boundary by boundary, a hidden architecture emerging from motion. This method also fits the tone of the Earth itself. The planet does not explain itself loudly. It does not turn transparent. It gives hints. It lets waves pass through it. It allows patient observers to notice where those waves speed up, slow down, bend, or vanish. The knowledge arrives indirectly, and perhaps that is part of why it feels so satisfying. It is not forced open. It is listened to. That is how we came to understand that the mantle is not uniform all the way down. It is how scientists identified major internal boundaries. It is how the outer core was recognized as liquid and the inner core as solid. The waves do not describe these things in words, of course, but they reveal them through behavior, through what reaches the far side of the planet and what does not, through which signals arrive and how they arrive altered. So the deep earth has been studied as much by absence as by presence. A missing wave can matter as much as a detected one. A delay can matter as much as a clear arrival. The Earth's interior is read through patterns, and those patterns become more meaningful the more carefully they are observed. The planet is not silent. It is subtle. And that subtlety changes the way we think about distance. The center of Earth remains unreachable in any direct sense. Yet earthquakes occurring on one side of the world can still help reveal what lies deep below the other side. The whole planet participates in this listening. One tremor can send information across immense depth, and faraway instruments can catch the clues. In that way, Earth becomes not just an object beneath us, but a body that can be sensed through its own internal motions. That brings us closer now to the method itself. Because not all seismic waves behave in the same way, and that difference turns out to reveal one of the most important secrets in the entire planet. Some waves can travel through both solids and liquids. Others cannot. The Earth gives away its hidden structure through motion, not by opening itself, not by allowing us to travel downward layer by layer, but by changing the way vibrations move through it. That is one of the most elegant parts of the whole story. The deep interior remains out of reach, and yet it does not remain entirely silent. It leaves clues in the behavior of waves, and those clues become more meaningful the more patiently they are followed. Two of the most important kinds of seismic waves are called P waves and S waves. The names themselves matter less than what they do. P waves are able to travel through both solids and liquids. S waves, by contrast, can travel through solids, but not through liquids. That difference turns out to be one of the clearest tools scientists have for understanding the deep Earth. The waves are not just signals from earthquakes. They are tests. Each one asks the planet a question, and the planet answers through what the wave is able to cross. This is where the hidden layers start to become more legible. If a P wave passes through a deep region, but an S wave does not, that tells us something important about the material there. It suggests that the region is liquid rather than solid. This is one of the reasons scientists concluded that Earth's outer core is liquid. When earthquakes sent seismic energy through the planet, the S waves failed to appear in certain regions where they would have arrived if the Earth were solid all the way through. Their absence was not empty information. It was evidence. That is such a beautiful idea. A missing signal can reveal something real. A silence in the expected pattern can become one of the clearest signs that the planet changes at depth. Earth's interior did not have to be seen directly to be understood in outline. It became visible through absence as much as presence, through what certain waves could not do as much as what others could. P waves also help deepen the picture. Because they can move through both solids and liquids, they continued farther, but they did not always travel in straight or simple ways. As they passed through different layers, their speed changed. Their paths bent. They arrived sooner in some places and later in others. Those changes helped reveal boundaries inside the Earth, not just between crust and mantle or mantle and core, but also within those larger regions. The waves became a way of sensing transitions that no human hand could ever touch. This is where the idea of shadow zones became especially important. There are regions on the far side of the Earth where certain seismic waves are weak, altered, or absent, because deep boundaries inside the planet have bent or blocked them. These shadow zones are not flaws in the data. They are part of the message. They show that Earth is layered, that different materials redirect motion differently, and that the planet's interior is full of thresholds where physical behavior changes. By studying where waves vanish, reappear, bend, or slow, scientists were able to build a picture of the unseen world below. So the Earth became readable through patterns in motion, not all at once, and not with perfect certainty in every detail, but enough to reveal the broad architecture of the planet. A thin crust, a vast mantle, a liquid outer core, a solid inner core. The hidden Earth, though never opened, became increasingly knowable through the behavior of waves passing through it. The planet remained closed, but not unreadable. There is something especially calming in that kind of knowledge. It is not forceful knowledge. It is not the knowledge of breaking into something and tearing it open. It is the knowledge of listening, of noticing how one kind of vibration travels where another cannot, of learning from the shape of a path and the shape of an absence. The Earth reveals itself in a gentle way, through consequences, through patterns, through the movement of energy inside its own body. And once those hidden layers became clearer, the question naturally widened. The mystery was no longer only what the Earth is made of. It also became what those deep layers do, how the mantle's motion reaches the crust, how the core helps generate the magnetic field, how the hidden interior shapes oceans, mountains, earthquakes, volcanoes, and the protected world at the surface. Because the deep Earth is not only a structure, it is a source of effects that reach all the way up into the life we know above. The deep Earth stays hidden, but its effects do not. By now, the descent has reached all the way down through the crust, the mantle, the outer core, and the inner core, and then turned back toward the surface through the evidence of seismic waves. But the story does not end in the depths alone. The most important thing about Earth's interior is not simply that it exists. It is that what happens there reaches upward. The hidden layers below help shape the world above. One of the clearest examples is heat. Earth still carries internal heat, both from its early formation and from radioactive decay within the planet. That heat does not remain trapped forever in the deepest regions. It moves outward slowly, and in doing so, it helps drive motion in the mantle. That motion, though quiet and patient, is part of the larger system that influences plate tectonics. So when we look at the shifting crust above, we are seeing the surface expression of a deeper process. That is why plate motion belongs in the story of the deep Earth. Continents do not drift simply because they feel like drifting. Ocean floors do not open and rearrange on their own. The rigid plates at the surface are linked to what is happening below them. Heat helps power the slow circulation of the mantle, and that circulation is part of the reason the lithosphere remains mobile over geological time. The surface world may seem separate from the depths, but it is not. It is connected through a chain of cause and consequence. And once plates move, the surface begins to change in visible ways. Earthquakes often happen where stress builds along plate boundaries. Volcanoes often form where plates pull apart, or where one sinks beneath another. Mountain ranges can rise where continental masses meet and push upward over immense stretches of time. So some of the most dramatic features of the surface world, the trembling ground, the fire of volcanoes, the lifting of stone into mountains, trace part of their origin back to deep interior processes. The surface is not inventing these events from nothing. It is responding to a planet that is active below. The oceans tell the same story. New seafloor can form at spreading ridges where material rises and cools. Elsewhere, older oceanic crust can sink back down into the earth at subduction zones. So the crust is not only thin and broken. In some places, it is also being renewed and recycled. The floor of the ocean is part of a long-moving planetary system, one in which the deep Earth helps keep the surface from becoming static forever. Even the magnetic field belongs here. Earlier in the journey, the field may have seemed like something almost separate, something extending outward into space. But it is part of the same deep story. The motion of liquid metal in the outer core contributes to Earth's magnetic field, and that field helps shape the magnetosphere, which in turn influences how Earth meets charged particles from the Sun. So the deep interior does not only affect rocks, continents, and volcanoes. It also contributes indirectly to the protected environment surrounding the planet. That is part of what makes the hidden Earth feel so significant. It is not merely buried history. It is present structure with present consequences. Surface life unfolds on top of systems rooted far below sight. The forests, coastlines, roads, ocean basins, sleeping towns, and quiet houses of the surface world rest above layers that continue to influence the conditions around them. The deep Earth is not a finished story beneath an unrelated sky. It is still involved in the world above. There is something calming in that continuity. The surface may seem like one realm and the interior another, but the planet is one body. What happens below eventually matters above. Heat rises outward, plates move, mountains form, seafloor is renewed, magnetic protection takes shape. The world we know is not floating on top of something irrelevant. It is resting on and responding to a layered interior that continues to work slowly beneath it. And perhaps that is why the ground can seem so quiet. Not because Earth is inactive, but because human life is brief. A person can live an entire life on one patch of crust and never feel the full scale of the motion below. The planet seems still mainly because its deeper movements unfold over spans of time so long that they pass gently beyond ordinary notice. The hidden Earth has been active all along. And even now, beneath the calm of the present surface, it continues. The Earth is not a finished object. It can feel that way from the surface. A mountain seems complete. A plain seems settled. A road laid across the land suggests stability, as though the ground beneath it has already become what it was always meant to be. But the deeper story is slower and more alive than that. Earth is still working. It is still moving heat outward, still reshaping itself, still carrying ancient internal energy through the layered structure below us. The planet continues to cool over time. That is an important part of the long story. Earth was far hotter in its youth, and across billions of years it has gradually lost internal heat. But cooling does not mean inactivity. It does not mean the interior has gone quiet in any final sense. A fire can fade and still remain warm. A system can change and still continue. The Earth today is not as hot as the early Earth, yet it still holds enough internal energy to remain geologically active. That activity can be seen at the surface if we know what to look for. Plate motion continues. Earthquakes still happen. Volcanoes still erupt. Mountains are still shaped by uplift and erosion. Seafloor is still created in some places and recycled downward in others. None of this suggests a dead planet or a frozen interior. It suggests a world still carrying out long internal processes, even if those processes are too slow to be fully felt in ordinary life. This is one of the most important perspective shifts in the whole video. We are used to judging activity by immediacy. If something changes quickly, we call it active. If it remains mostly unchanged during a day, a week, or a year, we begin to call it still. But the Earth does not measure itself by human impatience. Its activity unfolds across geological time. What looks motionless in a single lifetime can be full of gradual motion across millions of years. So the hidden Earth is not frozen beneath us. It is simply working at a timescale much larger than our own. That is why the planet can feel so calm and so restless at once. A hillside can seem stable while the plate beneath it moves. A quiet coastline can rest above a subduction zone. A sleeping town can sit on crust shaped by heat rising from the deep interior. The calm of the surface is real, but it is not the whole truth. Earth's stillness is often a surface stillness, a stillness of pace, not a stillness of process. There is something almost comforting in that. The world beneath us has not fallen silent. It is continuing. The planet remains unfinished in the best sense of the word, not broken, not incomplete, but ongoing. It still carries the energy of its formation. It still reshapes itself from within. It still moves materials, transfers heat, and changes the outer world through the patient labor of its interior. Earth is not merely a relic of ancient violence. It is a present system. And this ongoing nature helps explain why the surface keeps changing. If the deep Earth had truly gone still, the crust would tell a different story. plate boundaries would not remain active in the same way. Volcanic systems would not continue to form. The long tectonic rearrangement of the planet would not still be underway. But the evidence is all around us. The Earth remains geologically alive, not in the biological sense, but in the sense of continuing internal motion and outward consequence. That phrase matters here. Geologically alive. It reminds us that the planet is not just a stage where life happens. It is a participant in the conditions of life. The shape of continents, the rise of mountains, the recycling of crust, the magnetic field surrounding Earth. All of these are tied in one way or another to a world that continues to move below. We live not on a finished shell, but on the outer margin of an active system. And that raises a softer question now. What does it mean to live on such a world? To go through ordinary life, cooking, sleeping, driving, talking, worrying, resting, all on the thin crust of a planet whose deeper layers are still carrying out such long internal motion. Because once the scale settles in, the familiar world begins to feel slightly different. Not less safe, just deeper. All human life unfolds on a very narrow outer margin of the Earth. That may be one of the quietest strange facts in this whole journey. We spend our days in rooms, on sidewalks, in cars, in fields, on beaches, under roofs, among trees, along roads, beside rivers, across city blocks, and through all the familiar settings that make up ordinary life. Everything feels immediate there. The air, the light, the sounds of a neighborhood, the softness of a bed, the weight of a floor beneath your feet. The surface world feels complete because it is the only part of the planet we directly inhabit. And yet, it is only the outer edge. Everything familiar in human life happens on the crust, that thin outer shell resting above depths shaped by pressure, heat, chemistry, and time far beyond ordinary experience. Beneath the routines of breakfast and bedtime, beneath conversations and errands and sleep, the Earth continues downward into layers no person could survive, no hand could touch, and no direct journey could complete. The world we know is real and substantial, but it is also a surface expression of something vastly deeper. That does not make everyday life small in a sad way. If anything, it makes it more beautiful. A quiet kitchen at night, a dim road after rain, a sleeping dog near a doorway, a field under moonlight, a town settling into darkness. All of these ordinary scenes rest on the thin crust of a layered planet whose inner structure is still shaping the world above. The surface is not detached from the deep earth. It is supported by it, influenced by it, and in some ways protected by it. That connection runs through almost everything we have followed so far. The crust exists as the cool outer shell of a differentiated planet. The plates move because the deeper Earth still carries heat outward. Mountains rise, oceans open, and earthquakes occur because the hidden interior remains active. The magnetic field extends around the planet because liquid metal moves in the outer core. Even the broad conditions that help make Earth hospitable are tied, in part, to processes that begin far below sight. The world above is not merely placed on top of the world below. It grows out of it. So to stand on Earth is to stand on the outer edge of something vast. Not vast only across the horizon, but downward. Beneath every ordinary place lies depth. Beneath a front porch, beneath a sleeping city, beneath a quiet road, beneath a dark forest path. The Earth continues into hidden layers that do not announce themselves directly. That depth is easy to forget because the surface is so convincing. It feels like the whole story. But now that we have followed the descent, the surface becomes more interesting, not less, because it can be seen in context. There is something deeply calming in that perspective. The world does not have to explain itself loudly to be extraordinary. A patch of ground can simply be a patch of ground, and also the upper skin of a layered planet with a metallic heart. A quiet evening can simply be quiet, and also be unfolding above slow mantle motion, deep boundaries, and a magnetic field shaped by hidden metal far below. The ordinary world does not lose its peace when we remember the depth beneath it. It gains another kind of meaning. Perhaps that is one of the gentlest gifts of geology. It teaches that the familiar is often resting on the mysterious, not in a frightening way, but in a structural one. The world is more layered than it first appears, more connected, more ancient, more active at scales too slow for daily life to notice. And yet daily life remains what it is: cups on counters, shoes by doors, beds at night, neighborhoods dimming under evening light, all of it held on the outer margin of a much deeper earth. So after all this descending, the thought can now begin to narrow again, back from the whole planet to one place, one patch of crust, one road, one field, one sleeping town, one dark shoreline. The same surface as before, and not quite the same now that its depth has been quietly remembered. Because in the end, this journey does not leave us in the core. It brings us back to the ground above it. A road at night, a field after dark, a sleeping town with its windows dim, a shoreline where the water meets the land in a quiet, repeating rhythm. These places feel calm because, at the scale of human life, they are calm. The ground holds. The surface rests. The world seems settled enough to trust without thinking. And most of the time, that is enough. But beneath that calm surface, the earth continues. The crust beneath everyday life is only the outermost layer of a much larger structure. Below it lies the mantle, vast and hot, made of rock that can slowly deform across immense spans of time. Below that lies the metallic core, beginning with a deep ocean of liquid metal and ending in a solid center compressed by extraordinary pressure. Between these regions are hidden boundaries, transitions, and changes in behavior that no human eye will ever directly witness, and yet their existence shapes the whole planet above. That is one of the quiet wonders of Earth. The world we know at the surface is not resting on something simple. It is resting on something layered, something ancient, something still working. Mountains, oceans, plate motion, earthquakes, volcanoes, and even part of the invisible magnetic protection surrounding Earth all connect back, in one way or another, to these unseen depths. The familiar world is not separate from the deep Earth. It is the outer expression of it. And still, the planet remains mostly unreachable below. We cannot descend into the mantle. We cannot sail through the outer core. We cannot stand at the inner core and look outward through the layers above. The deep earth remains beyond direct human reach, and likely always will. But unreachable does not mean unknowable. Through waves, through motion, through the behavior of matter under heat and pressure. The planet has allowed us to understand something of its hidden structure, not by opening itself, but by leaving clues. So the Earth beneath us is both concealed and legible. It is a place we cannot enter, and yet it is not sealed off from understanding. Its layers can be inferred. Its boundaries can be sensed. Its effects can be seen at the surface and even high above the atmosphere. The deep Earth remains hidden, but not silent. It continues to shape the world in ways both dramatic and gentle, from mountain building to magnetic shielding, from drifting plates to the quiet stability of the ground beneath a sleeping home. There is something very peaceful in ending here, not in the center of the Earth, not at the edge of the core, not in the shadow zones of seismic waves, but back at the surface, back where human life actually unfolds. A bed in a room, a road outside, a dark patch of trees, a coastline under the night sky. The same ordinary world as before, only now resting in a slightly larger frame. Beneath every familiar place is depth. Beneath every step is a layered planet. Beneath every sleeping town is a world still carrying heat, pressure, motion, and memory far below sight. And yet the surface remains quiet. That may be the most comforting part of all. The Earth does not need to announce its depth every moment. It does not need to remind us constantly of the mantle, the outer core, the inner core, or the hidden boundaries between them. It simply goes on being what it is, a calm outer skin above immense interior space, a settled surface above slow and ancient motion, a world that feels still enough for rest, even while continuing silently below. So wherever you are now, under a roof, near a window, under blankets, beside a dark road, or somewhere the night has gone very still, you can let that thought soften rather than sharpen. You are resting on the quiet outer layer of a very deep world, and far beneath that quiet, the planet continues in silence.